Look at the top three blocks: initiation, propagation, closure. That is the life cycle of a fracture. Now look at the four elements below: pressure, fluid, stress, proppant. These are not steps. These are the forces that control every stage. Pressure creates the fracture during initiation. Fluid and pressure together control how it propagates. Stress controls where it goes and how it grows. And when pumping stops, proppant determines if the fracture survives or disappears. So the top row tells you what happens. The bottom row tells you why it happens. This lesson connects the two. Follow the sequence shown on this slide. You inject fluid at a rate higher than the reservoir can accept. Pressure builds in the wellbore. At a specific point, pressure exceeds minimum stress plus tensile strength. This is breakdown pressure. The rock fails. A fracture initiates. Now shift your attention to the stress system. There are three stresses: vertical, maximum horizontal, minimum horizontal. Here is the rule: fractures open perpendicular to minimum stress, not where you want. Where physics allows. In most reservoirs, minimum stress is horizontal. So fractures are vertical. This is not negotiable. You do not control direction. You design within it. Now the fracture exists. The question becomes, how does it grow? Look at the controls on this slide. Injection rate adds energy into the system. Fluid viscosity controls pressure at the fracture tip. Rock stiffness controls how wide the fracture can open. Stress distribution controls where the fracture can go vertically. Now look at geometry. Length. This defines how much reservoir you contact. In low-K reservoirs, this is the most important variable. Height. This determines whether you stay in zone. Lose height control, you lose the entire treatment. Width. This controls conductivity, but is the hardest to control. Now the key insight. You control rate and fluid. You do not control the rock or stress field. Real engineering is working within constraints. This slide defines success. Fluid has three jobs: carry pressure, open the fracture, transport proppant. Now the critical moment. You stop pumping. Pressure drops immediately. Formation stress closes the fracture. Completely. Everything you created disappears. That is the natural system. Now the solution: proppant. Solid particles are placed in the fracture. They resist closure. They keep the fracture open under stress. Now look at the scale difference. Formation permeability may be 0.01 md. Proppant pack is tens of thousands of md. This is not improvement. This is a new flow system. If proppant fails, the entire treatment fails. Look at the pressure curve. First peak, breakdown pressure. This is where the fracture initiates. After that, pressure drops to a lower level. This is propagation pressure, always lower than breakdown, because you are no longer breaking rock, only extending an open fracture. Now define net pressure. This is pressure above minimum stress. This is what drives width and growth. Too low, fracture stops growing. Too high, fracture grows uncontrollably. So pressure is not just measurement. It is your real-time control variable. This curve tells you exactly what the fracture is doing. Now look at this equation. Fracture width depends on rate, viscosity, length, and rock stiffness. But focus on one term, the quarter-root relationship. To double width, you need 16 times the input. So width is insensitive to design changes. Now look at Young's modulus. Stiff rock gives narrow fractures. Soft rock gives wider fractures. And this effect dominates the equation. So here is the truth. You cannot easily design width. The rock defines it. That is why in low permeability reservoirs, we focus on fracture length. Because length controls reservoir contact. Width only supports conductivity. Now apply everything together. Low permeability reservoir. Strong stress contrast. Good containment. Execution. Fluid injected above fracture pressure. Fracture initiates at perforations. Propagation controlled by rate and fluid. Proppant injected before shutdown. Outcome: fracture remains open, flow pathway established, production increases. Now tie it back to the four elements. Pressure created the fracture. Fluid propagated it. Stress controlled its shape. Proppant made it permanent. Remove one, the system fails. That is fracture engineering. Fractures form when pressure exceeds stress and rock strength. Propagation continues only with sustained injection. Stress defines direction and containment. Fluid controls how the fracture grows. Fracture closes immediately after pumping stops. Without proppant, there is zero sustained conductivity. Final insight: fracturing is not creating a crack. It is creating a stable, conductive system under stress. If any part of that system fails, the treatment fails. Now you understand how a fracture is created. You understand pressure, fluid, stress, and proppant as concepts. But design has not started yet. Because now the real engineering question begins. What proppant should you use? What size? What concentration? Because the fracture only works if it stays open under stress. That is Module 3, Lesson 3. And that is where performance is determined.